Okay, so like I was explaining, since this has no coefficient in front, meaning this enthalpy given here should be written like this as standard enthalpy. Otherwise, if there was a coefficient in front, there wouldn't have been a zero here. It would have just been enthalpy of formation. So every time you are looking at a given equation and they want you to find the standard enthalpy, as long as they say standard enthalpy, your answer should be 1 molar. You should be careful with this one. When you find that the answer of this is negative, it simply means the reaction is exothermic, all right? And when it is positive, it is endothermic. That's what that actually simply entails. And here is an example of a schematic diagram of the energy changes of a given reaction. So you have methane burning in oxygen to produce carbon dioxide and water. So when you are actually doing the enthalpy of a reaction, you will add the enthalpy of the products and the enthalpy of the reactions. So this particular reaction given here actually happens in steps. Whenever these particular reactions are taking place, they happen in atomic form. So every time you can check, you have a molecule here. Okay, so this is say methane, and this is an oxygen atom. So methane here, there's this given standard enthalpy there where this breaks, and then there's this standard enthalpy here where this also gives you this. Now, when the reaction is happening, it's not the whole molecule of methane as it is here that reacts, but it's atoms, meaning methane has to break into its individual atoms. So here are the atoms. This dark atom there is carbon, and the hydrogen atoms that were there in form of hydrogen gas. So here, what you have here is standard enthalpy of activation, A, okay, when this is activated. So you have enthalpy of activation. Since the bonds are breaking, it is shown as a positive there. And if you check, it is on the reactant end. Now, you don't need to activate carbon and molecules like hydrogen, nitrogen, because they exist in abundance in the atmosphere in that particular state. So like you can see here, their enthalpy is 0. Okay, so this is representing the enthalpy of oxygen. So, and then you have enthalpy here of formation. So HC, when you find it is written with a small letter c here, it means enthalpy of combustion. Okay, so even that here is you have delta D. Also, there is the enthalpy of dissociation of this is actually, yeah, D is dissociation when this water molecule is dissociating in individual hydrogen. So when it is dissociating, it is positive going in this direction, but this is forming. So it is formation of a water molecule. Now you can check this water molecule here has this particular enthalpy with a negative sign. When you're doing this calculation, the equation is not written like this. The equation is change in enthalpy of the reaction is equals to the enthalpy, the sum of the enthalpy of products minus the sum of the enthalpy of reactants. So you check for your reactant, it is positive. All right, so formation of this is positive. This is a value that you have. Now this is the reactants, and then these are the products. So what is the enthalpy getting to here, and what is the enthalpy getting to this? Since from the atoms to the reactants. Look, now, since this equation is going this side and not the other way, that is why it is positive. Otherwise, what you're going to be looking at is how is this formed from this atom. So that, since we'll be going on the other end, should be a negative, and therefore that is why we say minus the enthalpy of formation, or the sum of formation of reactants. So that is how the equation will be. And then when you press in your values, what you're going to find is you will keep these as they are given. Sum, you add what is on the reactant. So minus 394, then plus again minus 596. You add, it's a sum of the formation of this. So you add these two, they give you a certain value. And you add these two also, 75 plus 0, they give you a value. And then you place in your formula by starting from negative value of what you will get plus. Now, that is not going to be plus, it's going to be minus, because it's minus, it's products minus reactants. Then you put in the values you will get here, and it gives you the answer to this particular question. So this is the equation that I'm just from telling you. The sum of n is the coefficient, okay, what each reactant has. So for instance, this is 2. This is 2 for a water molecule. Let me come to a water molecule, because this is 0, so it's not going to show a difference. This is 2 for a water molecule, but what is given here is just for 1. Okay, so in your equation, most probably you're going to say 2 multiplied by what is given here. So if this is for 1 water molecule, but 2 are being produced, it will be times 2. So that is what this particular n means, the coefficient that is with a molecule of interest. So 2 is with this, and therefore this n is going to stand in for 2 plus whatever it is that the energy is for the formation of one of those particular substances. And then, so reactant minus products will give you the enthalpy of a reaction all the time. So this is what you're going to face. And then standard enthalpies of elements like iron, the ones that are in their pure form, like I've explained already, water and stuff, carbon dioxide, I mean, their enthalpies are mostly 0, and therefore we omit them all the time when you are doing such calculations. If you look at an element that naturally exists like that, okay, for example, aluminium, you will find it existing just as a metal, aluminium, but this one you won't find it existing as a metal, iron 2 oxide. These elements are combining to form this particular molecule. Therefore, for the formation of this one, the aluminium will be omitted. But that one of this one is not going to be omitted, because this element you will not find existing in nature like this. The same as iron. Iron exists like this in nature, and therefore its enthalpy of formation is 0. So in this particular reaction, if it comes like this, your main interest are these two. These have 0 value. So it is between this one minus the formation of that one. So you just concentrate on the formation of this one minus the formation of that one. This one and that one, naturally they exist like that, and therefore they will be considered to be 0. Oh yeah, there is an example of a calculation. So what is the formation of your reactant? So this is your reactant, negative of that. The formation of this is the negative of that. Like I told you, the formation of aluminium and the formation of iron are the same, and they are therefore 0. So when it comes to this particular reaction, it will just be between this one and that one. So what value of this do you have? This one minus the value of that one. So this is what is written here. That one minus the negative of that, and the answer is the negative of that. That simply means this particular equation is an exothermic reaction, and it will cause a rise in temperature, all right? Or the vessel being used is going to feel warmer. Another example is this one. They're still using the same principle that I'm just from explaining to you, and therefore you don't need to worry about that one. This particular question is on phase changes. And phase changes, remember when we were looking at phase equilibrium, we had actually seen that it is a change in state, okay, from one state to another, because each state is a phase. So if you check out this example, solid water turning into liquid water, since water is turning into a liquid, that is actually known as fusion, okay? Fusion, so that is the enthalpy of fusion. When ice melts into liquid, it is fusion, and this is the amount of heat that is required. Now look at the amount of heat required. It's plus this, so meaning fusion is an endothermic reaction. Heat is gained by solid water, and then it melts and becomes liquid water. Liquid water can vaporize and become gaseous water, and the amount of heat required to do that is known as the heat of vaporization. So you have this as the heat of vaporization required to change water into gas. If you check these two, they are both endothermic reactions, on the same molecule. Here, the molecule changes to liquid, and here it changes into gas. But look at the marginal difference in the amounts. Now, the differences in the amounts are brought about because the bonds that are being affected in these two processes are different. In the first process where fusion is happening, the bonds, the intermolecular energies between molecules are not being broken. They're just being expanded, okay? Here, intermolecular forces are just being expanded and not broken. That is why the energy is less than that of vaporization, because for vaporization, the intermolecular forces of attraction are actually being what? Broken. Therefore, to break will require a lot of energy than to just expand an intermolecular force. For example, hydrogen bond. When you're expanding a hydrogen bond, you will require a small amount of energy than when you want to break it, because when breaking it, more energy is needed for that particular activity. Hence, the difference in these two endothermic reactions that are happening on the same molecule. Okay, so here it is bond enthalpy and bond energy. So when one more of bonds is broken in a gaseous state, that is known as that energy that is going to be used, the energy that is going to be released when a bond is broken is bond energy. This bond here between two hydrogen atoms, the bond that holds them together is the bond energy, okay? So for them to be broken, this bond energy has to be given out, okay? So when you are breaking this particular reaction, the energy that is contained in the bond is the bond energy. Once that particular energy is given out, the molecules actually break and they exist in atomic form. And this is how it is. So chlorine is held by this amount of energy, and therefore for a chlorine atom to be broken, this amount of energy has to be taken in. So that is what that is. So this allows us to predict the likely change in a chemical reaction, the bond energy, like it were. So bonds of reactants are stronger than those of products, blah, blah, blah. They are explaining why you're going to find that when bonds are being formed, energy is negative, and when bonds are being broken, energy is positive because the reactants have stronger bonds than do the products when products are being formed. So energy will be absorbed to break the bond, and energy will be released to form the bond. I've explained this to you, and this is an example here. When you are breaking a carbon-carbon bond, this is the amount of energy that is required. When you are breaking a double bond, this is the amount of energy that requires. So the more the bonds between the atom, the higher the energy that is required to break those bonds, because the number is increasing, meaning the energy content of the bonds is increasing, and therefore to break them, a larger amount of energy will be needed. So this is what this particular part is trying to explain. Please.
So,
Yes.
If I say bond energy is the amount of energy required to break a bond, is that okay?
Sorry?
Sorry. If I say bond energy is the amount of energy required to break a bond, is that okay?
The amount of energy required to break a bond, that is not bond energy. Bond energy is the energy that a bond contains. The bond with which atoms are held together. That is what bond energy is. When you are breaking or separating, that is dissociation. Okay, so that is going to be the dissociation energy. But dissociation energy is equivalent to bond energy because the two energies are equivalent. When you want to break a bond, you have to add an exact amount of energy that it contains. But in definition, you shouldn't say bond energy is the energy absorbed. No, it is the energy contained in a bond. That's what bond energy is.
All right.
Here, bond dissociation energy is defined as the amount of energy required to break one more of covalent bonds in gaseous species. You get? So when you talk of breaking of bonds, you're talking about what? Bond dissociation energy. And it's going to be represented like that, change in D as it were earlier explained. So I've already explained this. Now look at the difference between the formulas. When you are using enthalpies, it is the reactants products minus reactants. Whenever you're using enthalpies for the calculation, it's products minus reactants. When you're using bond energy, it is reactants minus products. So the enthalpy of the reaction is equals to the bond energy of bonds broken, and bonds are only broken on the reactant end, minus the sum of the bond enthalpy of the bonds formed. So what is formed? So forming is on the product end, breaking is on the reactant end. When you're using bond energy, BE representing bond energy, this is how the equation should be written. When you're using enthalpies of formation, you are going to do product minus reactants. When you're using bond energy, reactants minus products. So the questions may seem to be a bit tricky if you are in a rush, but otherwise the questions are straightforward. Just look at what is asked. What have you been given? Bond energy or enthalpy? So this is an example where they are using bond energy. So they're just replacing the energies with what is given on the reactant side and what is given on the product end. And therefore, like I told you, when you're doing your calculation, these coefficients should be there. So for breaking these two bonds, the two hydrogen bonds. So for breaking one hydrogen bond, this is the amount of energy that is absorbed, or this is the bond energy that is available. One nitrogen, that is what is there. Since there are two hydrogens, that's why you can see a 2 there, minus, you only have one of these, so this is what you get. So you're going to have the bond energy to form two nitrogens. The bond between two nitrogen is this one. And then you have the bond between nitrogen and oxygen, which are 4, 1, 2, 3, 4. That is the 4 that you are seeing there. So this molecule has two different bonds energies. it has the bond energy between nitrogen and nitrogen and the bond energy between nitrogen and oxygen. So whenever a molecule comes like that, you have to be mindful of how it has come, because when they're giving you enthalpies, they'll give them in this form. Nitrogen, nitrogen, nitrogen gas, triple bond to nitrogen, nitrogen to hydrogen, and hydrogen to hydrogen. So it is going to come in this form and not in that form. So you have to ensure that each bond is accounted for. That's why, since we have 4 of nitrogen hydrogen bonds, we have 4 here, and the equation comes down to this at the end of the day. So this is just another example where bond energy is used. And when you have this sketch of an energy cycle, this energy cycle is an example of Hiss's cycle, okay? But when they ask you to sketch the energy cycle for from a particular reaction, this is how you're going to show it. So this is the dissociation energy. That is the dissociation energy when you are breaking the hydrogen bonds. So you show those dissociations and then you show these associations. So these are combining to form that. These are breaking to form these. So here it's just 1, but here it's 2 hydrogens. That's why it's 4H. And if you check on the energy, there it is. Okay. Nitrogen to this, there's no problem. Oxygen, when this is going to that, it's 0. Remember, hydrogen exists like this. So from here to here is 0. But 4 of these, if you check, 4 hydrogen are forming a bond with 1 carbon atom. That is where this 4 is. So that is how you're going to do that calculation, if at all you are asked. So in this particular example, I think what was asked is for you to find what this energy is for, CH, what is the bond energy here? Calculate the bond energy of the CH bond. So you write the equation as it were. Bond energy or change in enthalpy is equals to the bond energy of reactants minus the bond energy of products. So for the reactants, this is what you have. This going down and that going down, and then the enthalpy of formation of this is what you have here. Since 4 bonds are forming, that is 4 multiplied by that, and then you carry out your calculation. That is the answer that you get at the end of the day. So this is just examples of molecules and their bond energies for this particular question, and you will be able to answer following what you have here. So 6 gaseous atoms, water molecules are formed. Check, check, check. You have 1 OH bond. So 1 OH bond, but how many OH bonds do you have there? You have 2 in this one times that is 12. So in your calculation, it will be this multiplied by 12. Okay, it will be that multiplied by 12 to give you the answer. And then you can do the same with the rest, and you'll be able to find what this bond enthalpy is for your practice. Now, do you guys have any questions so far?
Link is clear, sir.
Okay, so that simply means tomorrow when we meet, we are going to discuss the tutorial sheet on kinetics. We're going to look at how you handle questions on that one. That's a Friday. And then on Saturday, how many of you guys are 7th days? Okay, so I think on Saturday we will meet 20 or 21 for a makeup session for this particular week, and probably on Sunday also around 21. But in these hours, what we're going to be discussing is going to be questions. Then on Monday, we are beginning a new topic. So Sunday, we will discuss which topic we will be doing, but tomorrow Our session will be questions. We will be doing tutorial sheet on kinetics. And then on Sunday, we will be looking at past question papers. And then on Monday, we begin a new topic. All right, guys, we meet tomorrow.